Hello students, I am Sachitrakar. Welcome to Cars Physics. This is my lecture 17 on electrostatics and we are continuing electric charge and electric field. In this lecture, we will discuss on electric dipole. Then what's an electric dipole? Okay, we will discuss about electric dipole, then electric dipole moment, then we will find electric field intensity due to an electric dipole. Then what's an electric dipole? Okay, let's consider this is a charge. We may consider a point charge. Okay, this is a point charge and this is another point charge. Okay, let's consider magnitude of this point charge is minus q and it has plus q. So two charges have equal magnitude q and q, but they are opposite in nature. One is negative, other is positive. Okay, this is the line joining two equal and opposite charges and this is their center. Okay, so from the center, let distance of minus q is L and distance of plus q is also L, means distance between these two charges is 2L. We do take distance between two charges is 2L. Thus electric dipole consists of two equal charges, means two charges of equal magnitude q and q and opposite in nature. Okay, just in simpler way you may say electric dipole consists of two equal and opposite charges. What's equal? Equal is magnitude. What's opposite? Opposite in nature. One is positive, other is negative, separated by a small distance. Okay, electric dipole consists of two equal and opposite charges separated by small distance. Okay, then what is concept of dipole? What is concept of dipole? Usually, molecule consists of atoms. Atom is electrically neutral, means atom contains equal number of electrons and protons. And as we know, charge of electron is equal to charge of proton, 1.6 into 10 to the power minus 19 coulomb, but they are opposite in nature. So, an atom consists of equal number of electrons and protons. So in an atom, amount of positive charge due to protons is equals to amount of negative charge due to the presence of electrons. Okay, so in an atom, there is a positive centroid. In an atom, there is positive centroid due to presence of positive charges, means protons, and there is a negative centroid due to presence of negative charges, means electrons. Okay, the atom in which positive and negative centroid coincide, that atom is called as non-polar atom. Okay, but in the atom in which negative and positive centroids are separated by a distance, in atom or in molecule, whatever you may say, in which positive and negative centroids are separated, called as polar atom. Okay, usually a polar atom consists of electric dipole. Okay, next, this is electric dipole. Then what do we mean by ideal dipole? Ideal electric dipole, the same thing, but one little consideration. Electric dipole consists of two equal and opposite charges separated by small distance. But when we think about ideal electric dipole, Ideal electric dipole consists of two equal and opposite charges separated by infinitely small distance. Means dipole is ideal if charge tends to infinity and distance between the charges means 2L tends to 0. If magnitude of charge tends to infinity and distance between two equal and opposite charges tends to 0, then the dipole may be called as ideal electric dipole. Okay, dipole. You may think about the molecules H2, water molecule, or HCl, as you have already studied in chemistry. They are electric, they contain electric dipoles. Okay. Then, next term, electric dipole moment. So, what a dipole can do? Dipole can produce electric field, as you have already considered. Electric field lines of force are from positive to negative. Okay. So, we have already represented electric field lines in the previous lecture. Okay, electric dipole can produce electric field. Also, when electric dipole is left in uniform or non-uniform electric field, it will experience force and it may experience torque. We will study all these things in coming lectures. Okay, then about electric dipole moment. Dipole moment. Dipole moment is represented by, electric dipole moment is represented by P. Okay. In simpler way, we just to know the magnitude and direction of dipole moment is a vector quantity. Dipole moment is defined as the product of magnitude of one of the charge. There are two charges, plus q and minus q. Dipole moment is defined as product of magnitude of one of the charge and distance between two equal and opposite charges, means product of q and 2L. This is magnitude of electric dipole moment, and we may multiply an unit vector n cap which shows direction of dipole moment. In physics, by convention, direction of dipole moment from minus q to plus q. And I think you know in chemistry, the conventional direction of dipole moment is from plus q to minus q. So in physics, we do take this convention, direction of dipole moment is from minus q to plus q. This is direction of dipole moment. Okay. So dipole moment is a vector quantity and its direction is from minus q to plus q, and units of electric dipole moment, charge is in coulomb and distance is in meter. Okay, coulomb meter. Accordingly, you can find dimensional formula. Okay, so this is about electric dipole and dipole moment. Then some terms. See students, this is the straight line which joins two equal and opposite charges of a dipole. This straight line is called as axial line. This is center of the dipole. Just draw a perpendicular. This is 90 degree. This straight line means the straight line passing through center of dipole and perpendicular to axis of dipole or axial line of the dipole is called as equatorial line. Okay, so we should have fundamental idea about axial line, equatorial line, dipole moment, direction of dipole moment, okay, units of dipole moment, etc. Okay, so this is about electric dipole and dipole moment. Next, question arises. See students, suppose this is an atom or molecule in which positive and negative centroids coincide. So this atom is, or this molecule is non-polar. Suppose we are considering about a non-polar atom. Can we convert non-polar atom into a polar atom? Oh yes. How can you convert? A non-polar atom can be converted to polar atom in the presence of external electric field. As we know, direction of electric field is from high potential to low potential, or in general way we may say direction of electric field is from positive to negative. Okay, let's place here this non-polar dipole in an electric field. Suppose this is a positively charged plate, this is negatively charged plate. Then direction of electric field is from positive to negative. Or simply, if this is a non-polar atom, plus Q, minus Q, you may place here a positively charged body, or you may place here a negatively charged body, whatever may be. If the dipole is placed, non-polar atom means, not dipole, if a non-polar atom is placed in a electric field, then it may be converted to polar atom. See, if this is positive, then it will attract the electrons to the near end. Okay, so this side will become minus Q dash left, and this side will become plus Q dash. Okay, similarly, if this is positive, this side, in this side, negative charge will develop because the electrons will be attracted to the near end, and at the far end, there will be positive charge. Let this charge is minus Q dash, this charge is plus Q dash. Okay, so this is about conversion of non-polar atom into a polar atom. Okay, then electric field due to a dipole. Okay, electric field, I am writing the complete heading, electric field intensity at end on position of a dipole. Electric field intensity at end on position of a dipole. Let's consider an electric dipole. Okay, our first step is to consider an electric dipole. Let the dipole is AB. This is point charge minus Q. This is plus charge plus Q, minus Q and plus Q. This is negative and this is positive. Distance between these two charges is 2L. This is center of the dipole. This distance is L. This distance is L. And this is axial line of the electric dipole. Okay, the straight line joining to equal and opposite charges is called as axial line of the dipole. Then what's end on position? End on position is any point. Okay, end on position is any point on the axial line of electric dipole. Let's consider any point x in positive direction of electric dipole. So electric dipole moment is from minus Q to plus Q. So this is positive direction of electric dipole moment. Okay, so dipole moment, so why do we consider dipole moment? Dipole moment determines the strength of electric dipole. Okay, dipole moment, generally electric dipole, strength of electric dipole is determined in terms of electric dipole moment. Okay, let's consider any point x on the axial line. So any point on axial line of electric dipole is called as end on position. So this point is end on position. Let this point x is at a distance r from the center of the dipole, and obviously distance of this point from plus q is this total distance from center to point x is r, and this distance from O to B is L. So from B to X, distance from B to X is r minus L. So I do write here distance of x from plus q is r minus L, and similarly distance of x from minus q. See students, AB, length of AB is 12. Again distance of x from B is distance between AO is L and distance from O to X is R. So this total distance means distance from A to X is R plus L. So this is the distance of end on position from minus q. So similarly distance of x from minus q is R plus L. Then we have to find the electric field intensity at end on position means at point X. Then general principle of electric field intensity is defined as force experienced by a test charge or force experienced by an unit positive charge placed at a given point. This is the given point at end on position. We have to find the electric field intensity at end on position. We may take this is unit positive charge. So where we have to find the electric field? Where we have to find electric field? We have to place on unit positive charge. Where we have to find the electric field? We have to place on unit positive charge. Then force on unit positive charge. Force on unit positive charge is electric field intensity at that point. Here the point is X. We'll place here an unit positive charge to determine electric field at point X. But dipole contains two equal and opposite charges, plus q and minus q. So at the given point X, there will be two field intensities, means field intensity due to plus q and field intensity due to minus q. So there will be two field intensities at point X, and we have to find resultant field intensity at point X, means resultant field intensity due to an electric dipole at end on position X. Okay, and we have already determined what is distance of X from plus q and what's distance of X from minus q. Then this positive charge will repel it. This positive charge will repel this unit positive charge. Let intensity is U1, and minus q will attract it. This is positive, this is negative, it will attract it. Let intensity is E2. Then field intensity or electric field intensity at X due to plus q. And as we know, electric field intensity, magnitude of electric field intensity is K Q divided by square of distance. You may take any distance. Suppose I am taking distance is x, K Q by x square. But here, electric field intensity at X due to plus Q, let's take field intensity is E1, magnitude of E1. K, charge is Q, divided by square of distance. Distance from plus q to x means distance of this end on position from positive charge is r minus l. Then here in place of x we will write square of distance r minus l whole square. Similarly, field intensity at x due to minus q. Let here field intensity due to minus q is E2, means minus q attracts this unit positive charge. Then magnitude of E2 is kq, charge is q, divided by square of distance. Distance of x from minus q is r plus l, then square of distance is r plus l. And as you have already seen, direction between E1 and E2 means E1 and E2 are oppositely directed. So angle between A1 due to plus q and E2 electric field due to minus q is 180 degree also. If you compare these two equations E1 and E2, kq divided by r minus l whole square, this is kq divided by r plus l whole square. So we may write magnitude of E1 is greater than that of magnitude of E2. So two vectors are in opposite direction. Magnitude of one vector is more than that of the other vector. Then, as per vector law, addition of vector quantities, I am erasing this. We may write magnitude of resultant field intensity is magnitude of E1 minus magnitude of E2, and obviously direction of resultant field intensity is along the direction of greater vector, means along the direction of E1. E1 is greater than E2, so magnitude of resultant field intensity is along E1. Okay. So now our aim is to calculate magnitude of resultant field intensity. Okay. So in place of E1, I can write KQ divided by R minus L whole square minus E2. E2 is KQ divided by R plus L whole square. This is very easy. KQ. Bring it common. Inside bracket 1 divided by R minus L whole square minus 1 divided by R plus L whole square. Then magnitude of resultant field KQ, LCM, R square minus L square whole square. Then here R plus L whole square minus R minus L whole square. Then magnitude of resultant field KQ, R plus L whole square minus R minus L whole square, it will come 4RL divided by R square minus L square whole square. So finally, so can I erase all these? Okay. We have already discussed about all this and we will solve here. Next. Then magnitude of resultant field intensity is KQ into 4RL divided by R square minus L square whole square, and magnitude is, see students, K into Q 4RL, I may break it 12 into 2R. 4RL is equal to 12 into 2R. Q into 12 into 2R divided by R square minus L square whole square, and magnitude of resultant field intensity is 2. K. Q into 2L. Q into 2L is dipole moment. Q into 2L is P into R divided by R square minus L square whole square. Okay. And as we know, since magnitude of E1 is greater than that of magnitude of E2, so direction of resultant field is along the direction of E1. So E1, direction of E1 is along positive x-axis. This direction is also from minus Q to plus Q. So direction is from minus Q to plus Q. Also you know, direction of dipole moment is from minus Q to plus Q. Direction of dipole moment is from minus Q to plus Q. Okay. So, or we may write or parallel to dipole moment. Minus Q to plus Q or parallel to dipole moment. So this is the formula for field intensity, electric field intensity at end on position due to an electric dipole. Okay. For ideal electric dipole, as we have discussed, generally electric dipole consists of two equal and opposite charges separated by small distance. But for ideal electric dipole, charge tends to infinity and distance between two charges 2L tends to 0. If 2L tends to 0, then for ideal electric dipole, this distance R is greater than L. So sometimes question is asked like this. An electric dipole consists of two equal and opposite charges separated by small distance. Small distance in comparison to what? Okay. As you know from very beginning, everything in this universe is relative, nothing is absolute. So, dipole consists of two equal and opposite charges separated by a very small distance. Very small distance in comparison to what? Very small distance. Distance between two equal and opposite charges is very small as compared to the distance means R, where electric field is calculated. So, distance between two equal and opposite charges of a dipole is very small as compared to the distance where we have to find electric field intensity. So, for ideal electric dipole, R is greater than 2L or R is greater than L. Here we have taken L, so R is greater than L, then take L negligible. Then in this case, magnitude of electric field intensity is 2 kpr divided by L is neglected, R square minus 0 whole square means R to the power 4. So finally we will get magnitude of electric field intensity is 2 kp by R cube. Again, direction is parallel to dipole moment. So at end on position, direction of resultant field intensity is from minus q to plus q or parallel to dipole moment, and in this case where I will write here where k is 1 divided by 4 pi epsilon naught. So this is about electric field intensity at end on position, or it's also called as tan A position, end on position or tan A position. Okay. Then next point, this is board based derivation and result is required. This result is also important for electric dipole for numerical point of view. Okay, this is also required for numerical point of view. Okay, both the formula are important. This is for usual dipole and it is for a very small distance, means for small dipole. Okay, or for if it is mentioned for ideal electric dipole. Okay, then next point, electric field intensity at broad side on position. Electric field intensity at broadside on position, or you may write it at tan B position of a dipole. Okay, this is about electric field at end on position. Then as we got electric field intensity at end on position due to an ideal electric dipole is 2 kp by r cube, and direction is from minus q to plus q or parallel to dipole moment. Okay, next. Now we will get electric field intensity at broadside on position of an electric dipole. Okay. Again, let's consider an electric dipole. This is minus q, this is plus q, dipole is AB, and this is center of the dipole O, this distance is L, this distance is L. Means length of the dipole is 2L. So we do take L and L. So O is reference point. From O to position of minus q is L, from O to position of plus q is L. So O is center of dipole or reference point. So as we have already discussed, this is axial line or axis of dipole. So this is equatorial line, means this line is perpendicular to axial line and passes through the center of the dipole. This is equatorial line. Then we have to find the electric field intensity at broadside on position. Any point on axial line is called as end on position. Any point on equatorial line is called as broadside on position. Okay, so this is equatorial line, this is center of the dipole. Let's consider any point y on equatorial line. This is broadside on position. Okay, any point on equatorial line is called as broadside on position of the dipole. Again, we have to find the electric field at this position. Let distance from O to y is r. In that case also, distance from O to x was r. Here distance from O to y is r. We have to find the electric field intensity at point y. Again, we have already discussed where we have to find the electric field. We have to place on unit positive charge at that point. Then magnitude of electric field is kq divided by square of distance. Okay, let's place here an unit positive charge at point y. Then distance of y, from plus q means distance by. See, this is a right angle triangle, this angle is 90 degree. Okay, so from right angle triangle OYB, base is L, perpendicular is R, then this is hypotenuse, means BY is hypotenuse. This is equals to square root of R square plus L square. Okay, similarly distance of y from minus q, again this is 90 degree. OAY, this is base L, this is perpendicular R, so this is hypotenuse, so this distance is also square root of R square plus L square. Thus AYB, these two sides are same, square root of R square plus L square, so this angle is equal to this angle. Let these two angles are theta each. Then we do place an unit positive charge at point y, where we have to find electric field. Here at point y there will be electric field due to plus q, and also there will be electric field due to minus q, means at point y we have to find resultant electric field intensity due to two equal and opposite charges of the dipole. Then this is positive charge. Let this positive charge repels. Since this is a unit positive charge, so this positive charge repels it. Let electric field intensity is E1 and this is minus q attracts it. Let electric field intensity due to minus q is E2. So here these two charges q and q, means magnitude of these two charges is same. Also distance from B to y is equal to distance from A to y, and both these distances are square root of R square plus L square. So electric field due to plus q is E1, magnitude of E1 is kq divided by square of distance by is square root of R square plus L square. So square of distance means R square plus L square. Square root of R square plus L square whole square means kq by square of distance, kq by R square plus L square. Similarly, electric field intensity due to minus q is E2, again distance is same, charge is q, so this is also kq divided by square of this distance means R square plus L square. So here magnitude of E1 is equal to magnitude of E2. Okay, this angle is theta, this angle is theta. Draw a line parallel to axial line. Okay, so if this angle is theta, see these two lines are parallel. AB, suppose this is any point y x dash. AB and YX dash are parallel. So this angle is theta. So this angle is theta. Also this angle is theta. Now we do have to resolve the vectors E1 and E2. Okay. E1 is resolved. Can I erase this? We have got it. Y x dash. Okay. Then component of E1 along y x dash is E1 cos theta, and component of E1 means another rectangular component. One rectangular component is E1 cos theta, other rectangular component is E1 sin theta. Similarly, we may resolve field intensity E2, this angle is theta. So component of E2 along y x dash is E2 cos theta, one of the rectangular component of E2, and another rectangular component is E2 sin theta. As we have discussed, magnitude of E1 is equal to magnitude of E2. So E1 sin theta is equals to E2 sin theta in magnitude, and both are oppositely directed. So vector sum means E1 sin theta plus E2 sin theta, both are of equal magnitude and opposite in direction, so their vector sum is 0. Means magnitude of vector sum of E1 sin theta and E2 sin theta is 0, since E1 magnitude is equal to E2 magnitude, and E1 sin theta, E2 sin theta, angle between them is 180 degree. Okay. Then we have already resolved these two field intensities, and these two rectangular components are added to give 0 resultant. Again, about these two components, E1 cos theta and E2 cos theta. See, angle between E1 cos theta and E2 cos theta is 0 degree. Means E1 cos theta and E2 cos theta both are along y x dash, so angle between them is 0 degree. So resultant electric field intensity, sum of these two rectangular components is 0. Again, resultant field intensity, magnitude of resultant field intensity, angle between E2 cos theta and E1 cos theta is 0. Then magnitude of E1 cos theta plus magnitude of E2 cos theta. Since both are in same direction, they are added to give resultant. Okay. Then magnitude of resultant electric field intensity is E1 cos theta plus E2 cos theta. See, E1, magnitude of E1 is equal to magnitude of E2. So we may write either 2 E1 cos theta or 2 E2 cos theta. Okay. Then this is equals to 2. In place of E1, we may write KQ divided by R square plus L square into cos theta. So magnitude of resultant electric field 2KQ divided by R square plus L square into cos theta. See, any of the right angle triangle, you may consider this triangle or you may consider this angle. Suppose I am considering this triangle, this angle is 90, this angle is theta. Then in this right angle triangle cos theta, OYB is the right angle triangle. In this right angle triangle cos theta is base divided by hypotenuse, means cos theta is base is OB, hypotenuse is BY. Then in place of cos theta we will write OB is L, BY is square root of R square plus L square. Then magnitude of resultant field intensity I am doing here. Magnitude of resultant field intensity is 2K 2Q into L. I may write it Q into 2L. 2KQL, Q into 2L into K divided by, this is R square plus L square. This is square root of R square plus L square. So solving it, R square plus L square whole to the power 3 by 2. So magnitude of resultant field intensity K Q into 2L, product of magnitude of one of the charge and distance between two equal and opposite charges is dipole moment P divided by R square plus L square whole to the power 3 by 2. Okay. Then what is direction of this resultant field intensity? See, electric field intensity, resultant electric field intensity is E1 cos theta plus E2 cos theta. Both are directed along yx dash. So resultant field intensity also directed along yx dash since angle between them is 0 degree. Yx dash, this is the direction yx dash means from plus q to minus q. So we may write direction is from plus q to minus q, or we may write direction of dipole moment from minus q to plus q as our convention in physics, but here we get direction of this electric field intensity from plus q to minus q means opposite to the direction of dipole moment, or we may write anti-parallel to dipole moment. Okay, so this is for electric dipole. Also we will get numerical on this formula. Now about ideal electric dipole. Okay, I will erase all this, not required now. Okay, for ideal electric dipole. For ideal electric dipole, I will not discuss more because you already know it. R, OI is R, distance is greater than 2L, or distance is greater than L. So for ideal electric dipole, magnitude of resultant electric field is Kp. Here L is neglected. L means L square is neglected. R square to the power 3 by 2 means R cube. Again direction is from plus q to minus q, or anti-parallel to dipole moment. So this is about electric field intensity at broadside and position. Simple comparison. Electric field intensity at end on position is equal to, for ideal electric dipole, 2 Kp by R cube, direction is parallel to dipole moment. Okay, electric field intensity at broadside on position. Electric field intensity at broadside on position, as we get here, Kp by R cube, and direction is anti-parallel to dipole moment. Okay, so at the end on position, electric field intensity is 2 Kp by R cube for ideal electric dipole, and direction is parallel to dipole moment. Electric field intensity at broadside on position is Kp by R cube for ideal electric dipole, and direction is anti-parallel to dipole moment. So by comparing these two, here 2 into Kp by R cube, but here Kp by R cube. Thus electric field intensity at end on position is twice, means 2 times, as compared to electric field intensity at broadside on position. So ratio of electric field intensity at end on position to that of electric field intensity at broadside on position, if you write it E tan A, here E tan B for broadside on position. So electric field intensity at tan A position, electric field intensity at tan B position is 2:1 or 2/1. So ratio of electric field intensity at end-on position to broadside-on position is 2:1 and they are oppositely directed. At end-on position, direction is parallel to dipole moment. At broadside-on position, direction is anti-parallel to dipole moment. Okay, so all these formula are important and the derivation is useful for your regular studies. Okay, in next lecture, means in lecture 18, we will have a discussion on electric field intensity at any position due to a dipole. Okay, then we are going very closer to end of this topic, means electric charge and electric field. Okay, thank you students, thank you for your sincere support. Thanks.